Hello. So in this video, we will be quickly going through the solutions to these 10 questions in the limits practice sheet. So the first question here is pretty straightforward. We look at that first of all, then we have a couple of questions here where we have to use either factorization or rationalization. Then we have some problems where you can have limits that go to plus or minus infinity. After that, we have three more problems where this time x, the value of x, approaches either plus or minus infinity, and we have to determine what the limit does. And then finally, we have two limits where we have to use the theorem that says as x approaches 0, the function sine x over x approaches the value 1. Okay, so in this video, we'll just be quickly going through these solutions just to identify the main things to consider when doing these solutions. More finer details will be given during the tutorial sessions. So we start with question one, which is very straightforward. Whenever you have a limit, and let's say it's a fraction like this, if you were to look here, the limit is as x approaches 1. If the limit of the denominator is non-zero and the limit of the numerator is finite, then this thing here is just a straightforward limit which we can just evaluate using some of the first theorems and properties of limits that we discussed in lecture 1. Right, so as x approaches 1, if we look at the denominator, we see that the denominator approaches value 2, which is non-zero. And also the numerator has a finite value. So we can simply work this out using the theorems that we did in class. Right, so like I said, this one is very straightforward. You would write the limit of this fraction here as the limit of the numerator divided by the limit of the denominator. That is one of the theorems that we discussed in class. And then you can easily evaluate these limits, again, using properties that we discussed. So in the end, we get the answer that the limit is negative a half. Okay, so that's pretty straightforward. Then we have the second question. Now, as x approaches 4, if we look at this function here, the denominator would approach 4 squared plus 4 minus 20 is actually 0. So the denominator approaches 0, and the numerator also approaches 0. We have 4 squared minus 16, which is 0. So in a case like this, we call this an indeterminate form. It's a form of 0 divided by 0. So we can't just look at the limit as it is and evaluate what the answer is. We have to do some more work first. And generally speaking, the methods that we would use for something like this are rationalization or factorization. Now, you would only use rationalization when you have something like a square root or a fourth root or an even root. There's no such term here. So what we need to do is try to factorize this. Right? So the numerator is easy to factorize. This is just a difference of squares, x squared minus 4 squared. So you can factorize that. And in the denominator, if you're not sure how to factorize this, then what you would usually do is use the fact that x approaching 4 makes this approach 0, which means that x minus 4 is a factor of this. So you could use polynomial long division using x minus 4 as a factor, or x minus whatever this number is, if you're not sure how to factorize it. All right, but in this case, we can factorize the denominator. We get x plus 5 times x minus 4. Then we cancel the x minus 4 from above and below. And now this is no longer indeterminate, so we can evaluate the limit to get our answer, which is, in this case, is 8 over 9. Question 3. So here we have a square root. So we have x square root of x plus 1 minus 2 over x minus 3 as x approaches 3. Now in this case, again, as x approaches 3, we see both the numerator and the denominator would approach 0. So this is again the indeterminate form 0 over 0. In a question like this, when you see a square root, the easiest thing to do is to try to rationalize this by, in this case, multiplying by the square root of x plus 1 plus 2. You could also factorize this. So I'm going to show you both methods, starting with the factorization method. So what you would do in a case like this is you notice there's an x plus 1 inside the square root. So it'll be helpful if we get that x plus 1 by itself in the denominator as well. So we can take x plus 1 and then we have to subtract 4 so that we get back negative 3. Right? 1 minus 4 is negative 3. And then in the denominator, we have this 4. We could think of this as 2 squared. And if I could write this x plus 1 as something squared, then I can use difference of squares. So what we do is we write x plus 1 as the square root of x plus 1 squared. Then we can use difference of squares to factorize the denominator. We cancel this square root of x plus 1 minus 2 above and below, and we end up with this term, which is no longer indeterminate. As x approaches 3, this function here approaches the value a quarter. So our answer is a quarter. Now, the second method is where we rationalize, which might be a little easier for most students to do. So like I said, we multiply above and below by the square root of x plus 1 plus 2. And on top, we end up with, again, this will be a difference of squares, we end up with, after we simplified, x plus 1 minus 4, which is x minus 3. All right, be careful in the denominator, make sure you put brackets around this x minus 3 to make sure that you have the correct expression here. If you leave out this bracket, these brackets here, then you would have the wrong thing because then you're multiplying this 3 by this term, but not the x, which is wrong. Right, now the x minus 3 in the numerator cancels with this x minus 3 down here. And again, we get the same thing as before, which gives us a quarter as the answer. All right, notice that we keep writing the limit until there's no longer an x involved. As long as the variable and the limit goes away, then we stop writing the limit. But before that, we have to keep writing it. Okay, so moving on, question 4 now. So this question here, notice that as x approaches 0, the denominator approaches 0. However, the numerator does not approach 0, right? Remember, these two questions, questions 2 and 3, were indeterminate because the limits were of the form 0 over 0, right? The limit of the numerator and denominator, if you work those out, it was of the form 0 over 0. But here we have a non-zero number in the numerator. So this is not indeterminate. Whenever you have something like this, where you have something non-zero in the numerator, but you have something that approaches 0 in the denominator, then what you need to do is try to determine whether this thing approaches plus infinity or minus infinity, right? In this course, when you get questions like this, it will be one of those two cases. The third case is where the limit just does not exist because as it approaches from one side, you get something different than from the other side. But in this course, we are not considering directed limits. So whenever you see a question like this, it will always either be plus infinity or minus infinity. So we need to figure out which one it is. And how we do that is by looking at the limit of the numerator and denominator separately and identifying the sign of each one. So in a numerator, which is usually the easier one to work out, we have a function here, x cubed minus 1. And now as x approaches 0, that is just going to approach negative 1, where we note that negative 1 is negative. Now for the denominator, as x approaches 0, absolute value of 2x, also approaches 0. But the important thing here is not just that it approaches 0, but what values does it approach 0 through? Meaning this function, absolute value of 2x, does it always take positive values or does it always take negative values as it gets to 0? In this case, because of the absolute value function, it will always be positive, right? As long as x is not 0, this is always positive. Remember, for a limit, we are not concerned with what happens at the point, only as we approach the point. And as we approach 0, this is always going to be positive. So it approaches 0 through positive values. Now what we have is a numerator that is negative, and the denominator is approaching 0 through positive values. And something negative divided by something positive is always going to be negative, which means that our answer is going to be negative infinity. If this was positive and positive, then we would get positive infinity. If it was negative and negative, we would get, again, positive infinity. Right? But as long as one is negative and one is positive, we will get negative infinity. Always remember, when your answer is negative infinity, the limit does not exist, and you must state that. Because in this course, we are only concerned with real numbers. So if something exists, it means it has a real value. Now, question 5 is a little more complicated. So you might look at this and say, well, since we are considering limits that approach either plus or minus infinity, then this whole thing is either going to be plus or minus infinity, right? But no, it's not. So if you look at the numerator here, as x approaches 1, e to the power of, well, 1 minus 1 is 0. So e to the power of 0 is 1. So the limit of the numerator is non-zero, right? But the important thing here is that it is not just that it's non-zero, but it is finite. Now for the denominator, what happens to ln absolute value x minus 1? Right now, you could think of the graph of ln of absolute value of x. So if we didn't have the absolute value, right, this is just a side note, but if we did not have the absolute value, if I just had ln of x, right, forget this 1 for the time being. If I had ln of x and x approaching 0, then the limit of ln of x would be undefined, because of the fact that as you approach 0 from the negative side, ln of negative values is undefined in terms of real numbers. They actually have they have complex values. But in this course, they're undefined. However, on the other hand, ln of absolute value of x as x approaches 0 is minus infinity, meaning it doesn't exist. But it still has a value. It's still defined as something, right? Negative infinity. And the reason for that is because ln of absolute value of x, it doesn't matter whether x approaches 0 from the left or the right, absolute value of x is always positive. So the denominator would approach, well, ln of absolute value of x would approach negative infinity. Now, we could actually use a substitution here in this limit of ln of as x approaching 1, ln of absolute value of x minus 1. We can use a substitution to make this into the limit of ln absolute value of x as x approaches 0. Right, so as I said before, this is the solution here. The numerator, the limit of this is finite. Notice I didn't say anything about positive or negative, I just said finite. And in the denominator, so what we're gonna do is use a substitution. So we're gonna this x minus 1 inside here, it would be nice if that was a single variable. So let y be x minus 1. Now as x approaches 1, y is gonna approach 1 minus 1, 0. So this limit, if I replace x with if I convert this from a limit in x to a limit in y, I'll get the limit as y approaches 0 of ln absolute value of y, which, as I just mentioned, this is minus infinity. Right? Remember, these variables here, this y here, this x here, these are already dummy variables. So if I take this second limit here and I replace y everywhere with x, does not change the value of it. So for so what I notice here is that in the denominator, I'm gonna get more negative values. The magnitude is going to get bigger and bigger, they'll be negative. Right? It goes to negative infinity. Also, I notice I have in brackets here that the limit doesn't exist because we have that is minus infinity. Now, one thing to note is whenever you have a finite number divided by something that is infinite, whether it's positive or negative, that is always going to go to zero. Right? Because you have something that is fixed, something that is finite, divided by something that is immeasurably big. And that always tends to zero. So our answer is zero. Note that because the answer is zero, it means that the limit exists. This limit exists, is zero. Right? So I did not say anything about does not exist in because that would be wrong. This limit here doesn't exist, even though this one here does not exist, the overall limit does exist. So we just say the answer is zero, and that's all. All right, so moving on now. We have question 6. Well, question 6, 7, and 8 are all where the limit is as x approaches negative infinity here, or positive infinity, and then here negative infinity again. So we have one of two cases. Now, in general, when you have a limit as x approaches plus or minus infinity, if it's just a simple ratio or fraction with polynomials, if there are no roots involved, no squares or fourth roots, then it's easy to just go ahead and use the method that we discussed in class, which is you identify the highest power of x in the denominator, in this case it's x cubed, and divide everything by x cubed. So in question 6, we can do that. Right? Divide everything by x cubed. Notice that x goes to negative infinity here, right? Not positive infinity, but it doesn't matter. So make sure you simplify it correctly. This x cubed is canceled, same as this. 3x over x cubed is 3 over x squared, 1 over x cubed, and then 3x squared over x cubed is 3 over x. Now we did a theorem in class that says as x goes to plus or minus infinity, which in this case we have minus infinity, the limit of 1 over x to the power n is 0. So using that theorem, in this case where n is 1 for this term, 2 here, and 3 here, we see that each of these three terms goes to 0. So our answer is just going to be 4. Right, so it's pretty straightforward. Now, when x goes to plus infinity, it doesn't matter whether we have any square roots down here, right? We just, again, follow the same method as before. So again, we look for the highest power of x in the denominator. Now here it's a little trickier to determine what the highest power is. So what I usually do is look for if there's any, it doesn't matter if there's any square roots or whatever, look for the term that has the highest power. In this case, that's the 9x to the power 4, right? So you ignore the plus 1. And then we ignore the coefficient of this. So we ignore the 9. And what we end up with is the square root of x to the power 4, right? You cannot ignore the square root. That stays there. So we have the square root of x to the power 4, which is x squared. And that is what we use to divide everything by. So we divide throughout by x squared above and below, and then we simplify it. Now be careful when you're simplifying the square root on the bottom. You can think of this x squared as the square root of x to the power 4, and then bring it inside the square root. Right, after you simplify, you should get something like this. And again, we use the same theorem as before. This time x goes to plus infinity, and these three terms go to 0. So our answer is just 0. Now, question 8, you have to be a bit more careful here. All right, so here we have to be very careful because we have x going to negative infinity and we have a square root inside here. Whenever you have x goes to negative infinity and you have a square root, you can't just simply square root or fourth root or anything, any even root. You can't just simply proceed as before. because you will get the wrong answer, right? So if you want to, just to see what I mean, you could try to work this out as before. And if you try to approach this using the same method as before, the answer you may get in the end is positive 3, right? When you work through it. So you may get positive 3 as the answer, but that is wrong, right? Notice that as x goes to negative infinity, square root of x squared minus 1, the x squared will get rid of the negative sign, and we have the square root of something that's very big minus 1. This will be positive, right? This will be a positive number in the denominator because it is square root of x squared minus 1. Now in the numerator, we have 3 times x, which is going to be negative, a very big negative number, plus 1. That's still going to be a very big negative number. So we have negative divided by positive. So this limit should be negative, right? And when we work it through properly, you'll see that the answer is negative. The answer is negative 3. However, if we did the approach as before, just without considering, without any consideration, if we just went into it using the previous method, we would get positive 3, which is wrong. Right? I'll explain when we go through it where the error is if you did it the initial way. So the correct looking for this, like I said, is you can't just simply go straight into it. As discussed in class, what you need to do is whenever you have x approaching negative infinity and a square root involved, you use the substitution y is equal to negative x. Right? What this does is as x goes to negative infinity, y will approach negative times negative will be positive infinity. So now there's no longer a negative sign out here. And once I get rid of this negative sign out here, then I could proceed as before. So using this substitution, whenever we see x, we have to replace it with negative y, right? Because if y is negative x, then x is negative y. So this x has to become negative y. This x has to also become negative y. Right? After we simplify it, this is what we end up with. Notice this is similar to the thing we started with, but it's different because there's a negative sign in front of this 3, which we did not have before. Right? So just note that. So again, now we proceed as before, we identify the highest power, in this case, highest power of y, which will be the square root of y squared. So y, we divide everything by y, right? And then this simplifies to what we have down here. And when we work it through, you'll see we get negative 3 as the final answer. Now, if we had done this without the substitution, when we did this step here, assuming that this was all x and this negative sign wasn't here, when we did this step here, when we write y as the square root of y squared, that is where the error comes in. Because if we did it with x here, right, and I divide throughout by x, and I write x as the square root of x squared, x goes to negative infinity, so x is negative, right? It's supposed to be a big negative number. But the square root of x squared is always going to be positive because the square root symbol is defined as a positive square root. So we're in that step where we would have used x as the square root of x squared is where the error comes in. We're really supposed to use x as a negative square root of x squared because remember when you take the square root, it's plus or minus. So in this case, because x goes to negative infinity, if we are going to replace x with something, it should be the negative square root of x squared. And to avoid having to deal with that in the first place, that's why we use the substitution. So as long as you use the substitution, it will work fine. But just remember, you don't have to use the substitution unless there's a square root. So as you saw with question 6, we have negative infinity, but there's no square root. We just proceed as normal and we get the correct answer. All right, this is correct. It's only when we see this square root here and we have negative infinity, then we have to use the substitution. All right, and then we get to the last 2 questions, which are, again, using the limit as x approaching 0 of sine x over x being 1. So the first one is sine x cubed over 3x squared. Right now, what I usually like to do with these questions is we know that we're going to be using this theorem, right? Sine, well, if in this case I have limit as y tends to 0, sine y over y is 1. Doesn't matter what the variable is, if it's x or y, z or whatever it is. So we know we're going to be using this theorem, which means that whatever I have inside the sine, I need to have it in the denominator as well. So I have an x cube inside the sine. I'll need to get an x cube in the denominator. Right? So what I'm going to do is I'm going to pull this 3x squared by itself. So I have 1 over 3x squared by itself, just to not confuse me too much. So I write it on the side here, multiplied by the sine x cubed. Make sure you keep it inside the limit though. You only separate your limits once you simplify this enough, and then you're ready to work it out. And then for this sine x cubed, what I'm going to do is multiply above and below by x cubed, because I want an x cubed in a denominator. But I can't just introduce that, right? If I introduce it in a denominator, I need to have it in a numerator as well. So this here is what I would do. Then I would take this x cubed in the denominator and write it under the sine x cubed. And this remaining x cubed in the numerator goes with this 1 over 3x squared. We could simplify that, and it gives us x over 3. Right? Now, at this point, I can't really simplify this anymore. So what I would do is use a theorem that says a limit of a product of two functions is just the limit of the first function times the limit of the second function. So I have the limit of this term times the limit of this one. Now for the first term, we use a substitution. So if I want to use a theorem, right, remember the theorem is sine x over x, I need to get rid of this x cube and make it a single variable. So I can let y or z or whatever you want, you can let that be x cubed. Now as x tends to 0, x cubed will also tend to 0, so y tends to 0. So we can take this first limit and rewrite it in terms of y. And this here is just a theorem. So the theorem says this is equal to 1. So we can use that and plug it back into this. So we have that the limit of the thing we started with is equal to 1 times the limit of x over 3. Now, the limit of x over 3 as x approaches 0, that's straightforward to do. We can simply evaluate that. All right, so that's just 1 times 0. So our answer is just 0. And then the last question here, again, x approaching 0, we have sine of tan of 3x over 2x. So again, from the time I see a sign here, sign of something, I know I'm going to have to use this once x goes to 0 or something like that. So what I'm going to do is use a substitution. So I'm going to have to, well, at the end, I'm going to have to use a substitution for tan 3x. But before I could even do that, I need to get this tan 3x in the denominator. So I need to start doing that. So like I said, what I would do is take this 1 divided by 2x, pull it on the side here, and multiply it by this. And then I introduce a tan 3x in the denominator. Again, I have to multiply above and below if I'm going to do that. And then write this tan 3x in the denominator under the sign of tan 3x. Right, this second tan 3x in the numerator, I can pull it with on top of the 2x. Right, once I did that, this here, I know that once I see sine something over itself, I'm going to have to use a substitution to work that out. So I could pull this as a limit by itself and then multiply it by the limit of the remaining terms. All right, now, so this will work out later on. So notice I'll leave this as it is throughout. Right, if you wanted to save time, you could simply work this out now and then substitute it back in so you don't have to keep writing it. Now for the remaining terms, so I have limit of tan 3x over 2x. If I were to try to evaluate that limit as it is, as x approaches 0, tan 3x would approach, well, tan 3x is going to approach 0. And 2x also approaches 0. So this is still indeterminate. But really and truly, you shouldn't use it as it is. You don't leave tan 3x as it is. what you should do is write it first as sine 3x over cosine of 3x, right? Because we know sine of 0 is 0, well, and cosine of 0 is 1. This is still going to be indeterminate, so we still have 0 over 0. So I'm going to need to do some more work here to figure out this limit. And again, once we see a sine, we know we're going to have to use a theorem. So this 3x, I'm going to need a 3x in the denominator. So what I do is I pull this 1 over 2x cos 3x by itself. And then for the sine 3x, I'm going to multiply above and below by 3x. Right, so we rewrite it like this. The 3x in the numerator goes with this term. And then like this one here, I can write this, well, this entire product, I can write this as the limit of the first term times the limit of the second term. This, again, we'll have to work out using a substitution. Now, this x here cancels with this x, and we end up with 3 over 2 cosine of 3x in the third term. Right, this we can easily work out because as x approaches 0, cos of 3x approaches 1. So this limit here is just 3 over 2. And this 3 over 2, I can write it at the front because I know what the answer is. So the last thing we need to do is work out this limit and this limit. We can start with the easier one, sine 3x over 3x. So we let y be the thing inside here. So y is 3x, and as x approaches 0, 3x approaches 0, so y will approach 0. Right, so we get our limit is just going to be this, which from the theorem says that is 1. Similarly, for the more complicated term, right, sine tan of 3x over tan of 3x, we can let z be tan of 3x. And similarly as before, this here, when we use our substitution, we'll end up with sine of z over z. As x approaches 0, tan of 3x approaches 0 as well. So z approaches 0. Right? And again, from the theorem, this is 1. So plugging these two into the overall limit was 3 over 2 times the product of each limit that we just worked out. So times 1 times 1. And our answer is 3 over 2. And that is it. Okay, so that brings me to the end of this video.